Yeah, so today we're going to talk about n-dimensional Euclidean space. We're going to finish off chapter 1 today and get started a little bit with chapter 2 even. So we're going to start here in section 1.5. And yeah, so let's jump right in. I want to start by answering the question, what is n-dimensional space? And we'll talk kind of just like we've been talking geometrically and algebraically. So far, we've been talking, when I say n-dimensional space, n is just some whole number, right? Some positive whole number. And so far, we've been talking about two-dimensional space and three-dimensional space. But today, we're going to talk about more generically just n-dimensional space for any n. So that includes higher dimensional spaces, right? Like 4 or 5-dimensional space. And I want to talk a little bit about, first of all, what is n-dimensional space even? So geometrically, we can visualize Euclidean space in the cases when n equals 2 or 3, right? This is what we've been doing. We've been taking 2 or 3-dimensional space, right? And working with that algebraically, geometrically, and I've been able to draw pictures or use, we can use computers to help us with that, especially in 3 dimensions. And we'll see some more of that today. But in higher dimensions, but it gets difficult in higher dimensions. Okay. We are going to learn some tricks for maybe helping with that. Maybe we can, maybe not necessarily like perfectly draw pictures of higher dimensional space, but maybe we can look at some parts of it, and then we'll learn some of those tricks actually when we start chapter 2. But in general, visualizing it is hard. But I think where the magic really comes in is in algebraically understanding these, because algebraically, when we looked at 2 and 3-dimensional space, all we were looking at was the collection of 2-dimensional vectors or 3-dimensional vectors, right, respectively. Algebraically, we can just change the number of coordinates we have, and that changes the dimension of the vectors. So algebraically, it's, oops, wrong button. It's a combination, or it's a collection. I guess it's the collection of what we would call n vectors, which are n-dimensional vectors. N vectors. And again, n vectors are just n-dimensional vectors. The way we would write this is we'd use the same notation, just v, with the little hat over it, or if we were typing, we'd use a bold v. And then we get the coordinates now, instead of just being x, y, z, or v1, v2, v3, we call them v1, v2, all the way up to vn, to the subscript. We've been using some of this. I haven't called it out properly, but we use this notation a lot, right? When we have a vector named v, the coordinates, instead of calling them x, y, z, we want them to kind of relate back to this, especially if there's more than one vector hanging around. So we call them v1, v2, v3. In this case, we might have more v's, more little v's. So v1, v2, v3, v4, v1, v2, v3, v4, v5, maybe up to, I don't know, 17 or something like that. Okay, so we can study as high dimension as we want. Okay, and this is the notation we use. And you might be wondering, like at this point, you might be pausing and saying, like, okay, said like 17 dimensions, and that seems like absurd, right? Like, why do we even need to study higher dimensional space, right? I can't, like, we live in three-dimensional space, right? I can kind of see why two-dimensional space is important. It comes up a lot, even in three dimensions. It comes two-dimensional geometry and algebra comes up a lot. But why study more than three dimensions if we live in three-dimensional space? Well, it turns out that a lot of things are actually higher dimensional, even if we can't visualize it, even if it's not living in the physical world. A couple of quick examples. So if you're, so mathematicians have been studying higher dimensional space for a while, a long time, historically. But then at some point last century, some really smart physicists realized that the universe we live in is not actually three-dimensional, because time can't be separated from space, right? So this is relativity. I'm going to butcher it because I'm not a physicist, but if you want to learn about relativity, you can study physics and learn from someone who knows more than I do. But basically, the premise, what they realized was that space and time had to be linked. So that added an extra dimension to our space. We had 3 dimensions of space plus a dimension of time. And so when you're studying relativity, you're actually studying this 4-dimensional space. And so that's one physical example of realizing, like, okay, yeah, we see 3 dimensions, but we also, when you actually incorporate time into that, you're studying a 4-dimensional space. So there's a good example of realizing, like, okay, well, now we have to know how to study 4-dimensional calculus, which we're going to learn today. You know, it's actually not much harder than 2 or 3-dimensional calculus. Or I guess we're going to learn this quarter. I shouldn't say today. We're not going to learn all of that today. But some other examples, maybe less physical, because then you can make the argument, okay, why not stop at 4? Well, it turns out that you can think of these coordinates as just like variables, right? So if you have a function with 2 variables, that's, you can say that the domain is 2-dimensional space. If it has 3 variables, it has 3-dimensional space. If it has 4 variables, it's 4-dimensional space. In the case of that physical example I gave, those 4 dimensions just have some physical meaning. But you can easily imagine in any discipline, it doesn't have to be physics. I think I was watching a lecture once where someone was working on a problem in biology, and you have all of these parameters. I think he had, you know, over a dozen parameters. And when you start doing work, you know, like actual trying to parse data that has to do with all of this, and you have all of these parameters, what you're really doing is dealing with problems in higher dimensions. And so you could think of the number of dimensions as the number of parameters you have in a certain problem you're working out. And so that's one way that's another thing that you can use this for. So that's like an example of yeah, if you're of using this in using higher dimensional reasoning in other disciplines. Does that make sense? Yeah, so it may seem silly to think higher dimensions higher than 3 because you can't even visualize it, but it can be incredibly useful once it actually comes down to solving problems. Okay, now in this class we learn it pretty abstractly. We don't always apply it to things, but it's a way of building that intuition so that you can apply it to things. Okay, cool. If you have questions, feel free to slow me down, but I'm going to move on to the next page here. Okay, so we've been studying a lot of R2 and R3, 2-dimensional and 3-dimensional space. Remember, this was our shorthand. So I guess one thing I can say is, you know, n-dimensional space. Maybe before I move on, I can add here, n-dimensional space is Rn, right? So that's one thing I will remind us. I mentioned that, you know, a couple. I mentioned R2 and R3 back in, you know, first or second lecture, but here is we can compare Rn and see, okay, we had a bunch of stuff we've been learning about in R2 and R3. How much of that gets transferred when we go to higher dimensions, right? And it turns out a lot of it does. So for example, the inner product does, right? So we can say V, if we have V, v and w, we can take the dot product, right? The inner product, dot product, different words for the same thing. And the fancy way we would write this is using this notation of the sigma, which is when you take a big sum, right? So this goes from, this is saying I goes from 1 to n of v I w I. Now that's fancy notation. Let's write that out a little more explicitly. Basically, remember when you take the dot product, you just take the first coordinates and multiply them. Take the second coordinates and multiply them. Oops. 2. And so on and so forth. And you're adding these all together as you go. So you keep going until you get to Vn Wn. Now, one thing to notice here is that V and W have to be the same dimension, which was the case when we were dealing with 2 and 3 dimensions even. But in the inner product, when now that we're dealing with higher dimensions, it's even more important to make that distinction that V and W have to have the same dimension in order to take their dot product. Okay, so the dot product works exactly the same way, except if there's more coordinates, you just do it. You have more terms in your sum that you're taking. And naturally, the length of a vector is also going to work. So here is, remember, it's the square root of the dot product of the vector with itself, which is just to say that it's the square root of v1 squared plus v2 squared, etc. Okay. So this is the square root here. This is the norm. This is the length or magnitude. Remember, those are all the same here. Okay. Again, the formula looks very. If you just let n equal 2 or n equal 3, it's the same formula we've been dealing with so far. Okay. Cool. Okay. Now we have standard basis vectors, which, if you remember, those are your ijk in someone's asking in the chat, where do I get I from here? So this I is just like a placeholder variable. This is, again, if you remember, sum notation. I'm introducing this I just because I is going to be the thing that goes from 1 to n. So it's just like this placeholder for us for the sake of the notation of this sum here. But if you're not super comfortable with the sum notation here, then this is just another way of writing all of this right here. Okay. Cool. Now the standard basis vectors, like I said, in 2 and 3 dimensions, it's the ijk, or I guess in 2 dimensions, just I and j. But in higher dimensions, we're gonna run out of letters, right? If we do ijk, maybe you're like, oh, maybe an L or M, and then like eventually you're gonna run out of letters if you do that. So the way we do it in higher dimensions is we use this notation E1 is equal to the vector 1 and then a bunch of zeros, right? E2 is equal to, again, I'm using this little hat. If it's typed, it might be bold instead. The little hat, remember, means unit vector. So these are unit vectors in particular. So now in E2, the second coordinate is a 1 and everything else is 0. And you can just keep doing this. So then like you'd go all the way up to En. Okay, so there are n of these standard basis vectors, as we call them. Someone asked last time why it's called a basis. Maybe you're wondering why it's a standard basis. And I talked a little bit about it last time, but I think if you're really curious about all that, a class like linear algebra would be where you would learn more about what all of these words mean. But for now, you can just kind of take it as like, this is what we call these vectors, is the standard basis vector. And some of you, I think some of you mentioned in that get to know you thread that you've taken that class before. So you kind of know a little bit more about what that means. So in particular, for example, in R3 here, for these vectors, there's n of them, but in R3, you have E1, but that's just your I vector. E2 is your J vector, and E3 is your K vector, right? So you have E1, E2, E3. Again, just another sort of notation thing. Okay. Cool. Any questions about all of this? So I wanted to focus in a little bit on the dot product now that I have all of this written down, and mention just in passing here, because I don't want to run out of time here. But I want to mention that the dot product has certain properties that they work in 2 and 3 dimensions, but they also work in higher dimensions. But I don't have time to go through all of them. But if you're like wondering something about, like, at some point you like are doing something with the dot product and it's something you're like, why isn't this working? And you want to look at some properties of the dot product, you can look in section 1.5. There's a theorem. It's theorem number 3. And I didn't write down the page number, but it's in the textbook there. So you can check that out. And it just talks about the dot product and kind of what properties it has. And so you can look at that there. Okay, cool. And then naturally, there's some formulas for stuff that we've seen before. But this slide is mostly just to say kind of the continuation of this slide, like all of these formulas still work. So the Cauchy-Schwarz inequality and the triangle inequality, right? So the triangle inequality was that you have x plus y is less, the norm of x plus y is the less than or equal to the norm of x plus the norm of y. And then the Cauchy-Schwarz inequality is also going to work in higher dimensions here. And I should write that down. I didn't write that down. Also these should be vectors, right? X and Y are vectors here. And again, if you remember the triangle inequality, it's kind of saying that this plus this, like the sum of those vectors is just this part here. So of course this is going to be shorter than going here and then going here, right? Which is to be expected. Yeah, Cauchy-Schwarz inequality. So one thing I want to point out about both of these is that the Cauchy-Schwarz inequality and this inequality are going to look the same as they did when we talked about them in earlier sections. So this is like x and y. These are vectors. When I take the dot product, this is just a number. So this is just the absolute value. But I can just start by taking the norms. And that's also going to give me, now this is just multiplication of real numbers. So this number is smaller than or equal to this number. Now these are going to look very similar to the first time we wrote them down. And that's because of the notation we use with vectors, right? Because these are just vectors, right? The difference is in this slide, these vectors can be 4-dimensional or 5-dimensional, whereas before they were either 2 or 3-dimensional. Okay. And now similar, another formula that we had before but still works in higher dimensions is the cosine formula, or the angle formula for, so the dot product of 2 vectors is equal to the product of their norms times the cosine of the angle they form between each other. So it's just that, we might be living in more dimensions, but they're still going to have an angle, but any 2 vectors are still going to have an angle between them. Okay. And if we want to turn something into a unit vector, that formula also hasn't changed. So you take u, if u is a vector and you want to normalize it, u hat, which is the normalized version of this, is equal to u over the magnitude of u. Okay. Cool. So all these formulas still work in higher dimensions. This slide is just kind of a reminder, like, hey, remember all of these that we learned about in 2 and 3 dimensions? They still work in higher dimensions. Okay. Now, some stuff that doesn't work, I think the big thing that doesn't work in higher dimensions is the cross product. So the cross product was specific to 3 dimensions. I mentioned it back then, but I'm going to mention it again. The cross product only makes sense if you're talking about 3-dimensional vectors. Okay. That might even be worth saying. So writing down, I should say. So cross product only works in R3. So only for 3-dimensional vectors. Okay. Cool. How am I doing on time? Okay. Cool. So let's move on here. So I don't get too caught up on these formulas. Yeah, these formulas, again, mostly just review. What we really want to spend some time talking about in this section is matrices. In other words, a matrix. We talked a little bit about them when we talked about determinants, right? But here we want to get to a more general notion of matrices for different dimensions, right? So here I have a big empty matrix here, and it's going to be the way we read this is M by N matrix, okay? And the way I remember what these letters mean is that the row always comes first. This is the number of rows, and then this is the number of columns. So I mentioned the little mnemonic, which is, right, you have RC, so you can think race car, or RC Cola, the soda thing, right? That's kind of how I will remember the order of these here. So for some reason, someone a long time ago decided, okay, the first number is going to be the number of rows and the second number is going to be the number of columns, which I don't always like, but I guess it works as long as we're all on the same page. And so this matrix here is going to have M rows and N columns. So here in the top, we start with A11. Remember, the subscripts here are 2 numbers, but it's not 11. It's 2 ones. It's 1 1. And those numbers represent the row and the column that it's on. So this is in the first row, first column, and it's going to go all the way over here to the first row and the last column. So that should be an N, because there are N columns in total. Okay. And then if you go down here, you're going to end up with AM1, because it's in the last column, which is, there are M of them. Sorry, it's in the last row, and there are M rows. So, but it's still in the first column, and then all the way down here, you get AMN. And so you end up with this. Here is your matrix. And this is very common, what you're seeing here, where I highlighted a few here, and then we just put dots everywhere in between to kind of say like, oh, and it just kind of follows that pattern. Okay. So some notation here, first of all, to point out, we like to use capital letters if we're referring to the matrix as a whole. So this is A, the capital letter refers to the matrix as a whole. And then if you want to save some space and you don't want to necessarily write the whole matrix, sometimes I'll write something like this: A is equal to little a I j, where this is just kind of a generic term. This is the ij term. So it's just some random term, some random entry in this matrix. I shouldn't say random, I should say arbitrary entry in the matrix. So I is the row and j is the column. Okay, so sometimes this is going to be like a formula, because you're going to have some formula for determining which, like based on the row and column, what is the actual entry going to be? Okay, cool. And we'll see this in action. I think that'll help start clearing up what the notation means. Okay. Any questions so far? Okay. Cool. So you've probably seen matrices before. We saw 2 2x2 and 3x3 matrices. Now we're going to see m by n matrices, which means they might not always be the square, right? Squares when they have the same number of rows and columns. Here they might have more rows than columns or vice versa. And what we're going to see in the next slide here is that we can multiply rows or matrices together in certain cases. So notice down here I'm highlighting the size of these matrices. So for example, you on the right hand, focus on the right hand side, you have these two matrices. You have an m by n matrix and an n by p matrix. Okay, and so that means you can multiply them together because these two numbers match. So the number of columns needs to match the number of rows. Okay, so these match. These match. Okay. And since these match, you can multiply these matrices together, and the output is going to be the leftover stuff. So m by p, you can kind of think of the ends canceling, but you need to have them on both. Okay. And now, how do we actually do the multiplication? Okay, so here I've set up my my matrices in a certain way. I've highlighted. We have our big matrix. It looks like this, but I've taken. Let's just focus in on this little guy here. So we have C, I, J. This is the ijth entry of this matrix, which just means it's in the ith column and the jth. No, sorry, ith row, jth column. See, it still mixes me up. And how do we get that from all of this information? There's a bunch of numbers over here. Well, what we're going to do is we're going to take AI1 and multiply it by B1J. Okay, so we took this and multiplied it by that, but then we're not done. We're going to add to that AI2 times B2J. Okay, you might see where we're going with this, maybe, but maybe not quite yet. But basically, what we're doing is the I and the J are going to stay the same on the B, on the A and the B, but the 1 here turns into a 2, then it turns into a 3, and you keep going until it turns into an N, right? And that's the last thing in this row. So we're going down this row for the A's and going down this column for the B's. Okay, and you might recognize this formula a little bit, right? This number is equal to the product of two numbers plus the product of another two numbers plus a product, and there's n terms here, right? This looks a lot like a dot product here. So what we're actually doing is to find a certain entry in the product here. We take a dot product of this row with this column. So you're going to do a dot product here, but the way you figure out what dot product you do is you say, okay, I want to find the ith row and jth column here. I want to find that entry. So I take the ith row of my first matrix and the jth column of my second matrix, and I put them on top of each other. So this is kind of what I usually picture in my head. So it's maybe reflected for you. So you have kind of these two matrices here, and you're multiplying them together. So you take the row in this matrix and the column in this matrix, and you kind of throw this on top of it like that. So you kind of throw this on top of it like that, and now you're taking a dot product on top of it. That's kind of what I'm picturing when I do this. Okay, and so you're multiplying these two together. Okay, cool. Any questions on that? we're going to jump right into some examples of this. So let's, and I think that'll help clear it up, because sometimes when you see all these like letters and the dots, it can get kind of confusing, and it helps to just have actual numbers in the place. So let's take a look at that. So here I have a few examples. Let's go through one and then take a little break and then come back and do the rest. Okay, so let's look at number one here. So number one, so you have 1, -2, 2, 1. Okay, and 1, 1, 1, 0. Okay, so if I want to compute this product here, then I'm going to get, so I have 2 by 2. So I have 2 by 2 and 2 by 2, right? Which means I'm allowed to multiply them together. All here is a bunch of 2s, so I'm allowed to multiply them together. But the important thing is that the number of columns, or sorry, the number of columns here matches the number of rows here. So columns matches rows, okay? And because of that, then I'm able to multiply these together. And now my answer is going to be 2 by 2. And in here, the way I'm going to multiply these is I'm going to say, okay, if I want to get this first entry here, the top left, that's first row, first column. So I take the first row of this matrix and multiply it by the first column of this matrix. So I'm taking this 1, 2 and multiplying it by 1, 1 as a dot product. So 1 times 1 plus 2 times 1. Okay, so this times this plus this times this. Taking this first row, multiplying it by this first column as a dot product. So times. Okay, now if I want the first row, second column, I'm going to still take this first row of this first matrix. Now I'm going to take this second column of the second matrix. So 1 times 1 plus 2 times 0. Okay. Now I'm going to, for this one, let me highlight it specifically. I want to figure out what goes here. Okay. So I'm going to take, that's in the second row and first column. So I'm going to take those two highlighted. I'm treating these as vectors, like -2, 1, and then 1, 1. And I'm going to take their dot product. Okay. And the answer there is going to be -2 times 1 plus 1 times 1. Okay. And now I have one last entry to figure out. It's this second row and second column. Second row, second column. So I do that. And so I get -2 times 1 plus 1 times 0. Okay. And if I simplify this, then I'm going to get, let me do that in my head. So we have 3, 1, -1, and -2. You can double check my arithmetic there just to make sure I got it right. But so yeah, so the product of these two matrices is equal to this matrix. And as we get going, we're going to get better and better at doing these sort of simplifications here and doing this matrix multiplication. Okay, cool. Any questions on that? For each cell, is it like a dot product? It's exactly like a dot product. So this highlighted box here, this cell here, I like the word cell, thinking of like a spreadsheet or like a table in Excel or something, and you call it a cell. So for each cell, you're taking taking this row as a vector and then this column as a vector and taking their dot product. Okay. So this here is a dot product of these two vectors. That's the next question is, we're basically multiplying each row by its corresponding column. So the column doesn't necessarily correspond to the row. The row and column both correspond to the cell or the entry that we're looking at in the final answer matrix. Okay, so this, so the fact that we chose the second row and the first column is because if you look at where this is in the final matrix, it's the first row and, sorry, it's in the second row and the first column. Second row, first column. Okay. Since they can be represented as vectors, does the answer matrix have a significance graphically? That's a good question. The answer is probably yes, but it's a little, yes. So in this case, in the 2x2 case, in the higher dimensional case, it's definitely harder to visualize. But in the 2x2 case, basically each vector, and we're going to get to this in a little bit, hopefully after the break. Each matrix you can think of as a transformation of two-dimensional space. So each of these matrices is doing some kind of geometric transformation of two-dimensional space. So you can picture it like I have these vectors and then it does this to those vectors. And what this is doing is it's basically applying, this final matrix is the same as applying both of those transformations. Okay, it's a little more complicated than just like a little picture. Okay, let's jump back into a few more examples. So here we have these. Here's another 2x2 example. Let me run through this one real quick. So let's see, we have, I think I'm gonna need a little more space, of course. So here we have the second example. Again, it's a 2x2. Maybe I'll just copy and paste here. There we go. So we want to do these two 2x2 matrices. Again, their product is going to be another 2x2 matrix. This one I'm going to go through kind of quickly, and then you can just kind of check in to see how, to make sure that you're understanding what I'm doing. So again, first row, first column. In this, that's this entry here is going to be the first row of the first matrix and the first column of the second matrix. And so we do the dot product of those, and we get 1 times 1 plus 1 times -1, which gives us a -1. And notice that these matrices are just the same two matrices we had before, but the order is switched in which we're multiplying them. And that's going to be important here. And now if I want to do up here, the top right, that's going to be first row, second column. Do the dot product there. That's 2 plus 1, which is 3. Okay. Now, if I want to do this bottom left, that's second row, first column. Do that dot product. I get 1 plus 0, which is 1. And then second row, first column here, the bottom right entry here, that's, again, like I said, second row, second column. Take that dot product, it's 2 here. Okay, so that's these here. That one I kind of flew through. I'm not, if you couldn't keep up with that, write this to answer down and then go and do it yourself, show your work, and make sure that you get the same answer when you take it slow. Okay, don't worry, I won't go this fast for the other one. I just wanted to breeze through this one. And the one thing I wanted to highlight here with this is notice that these are not the same matrix. So multiplying two matrices in a certain order, so the sort of general statement here that I'll make is that AB is not equal to BA. And we'll talk, I think I mentioned this a little bit more in the next slide. Okay, so AB is not equal to BA, okay, which is kind of different from the normal types of multiplication we're used to. Okay, I'm going to copy this last example down here so that we can work on it. Hopefully I have enough space here. Okay, let's work on this example here. So this one's much bigger, right? So first of all, how big is the final answer going to be? Well, let's see. This is what would we call this? This has 4 rows and 3 columns. So this is a 4x3 matrix. So this is 4x3. Now this one here has 3 rows and 2 columns, so we'd call this 3x2. So based on that slide, I had a couple of, what I had written on a couple of slides ago, how many, how big should the resulting matrix be here? Maybe I'll write it down here. So we have 4x3. And 3x2, the 3's match up, which is good. That means that these are compatible. We're allowed to multiply them in this order. Okay, but what should the answer be? Yeah, so someone in the chat's got it. 4x2, right? So the 3's match up, so you can kind of think like, they kind of like they match up, so you can they kind of get canceled or whatever, and you end up with 4 and 2. So 4 by 2 is what's left over. Okay, and we're gonna see that. How do you remember like how you match things up? Well, in this order, you see that in each row has 3 entries, and over here each column has 3 entries, and that's going to be nice for taking the dot product, right? So we're going to end up with a 4 by 2 matrix. So 4 and 2 wide. So 4 tall, 2 wide. Okay, and let's do that. We want to fill each of these in. So if we want up here top left, that is first row, first column. So we're going to take this dot product with this. So maybe I'll show some work off to the side, and then I'll fill in the entries as I go. So this is the -2 times 4 plus 1 time, or plus, yeah, that should be a plus, plus 1 times 0 plus 3 times 5. Okay, so it's the dot product of this row with this column. That simplifies to -8 plus 15, which is going to be +7. So you get a 7 in this entry here. Okay. Now let's kind of move like we were reading this page out of book. So from this entry, we go to the top right entry. It doesn't matter the order in which you do these. In fact, you can just skip around and say, I'm just going to do this one because we know exactly how to do it, just the row and the column. But I'm going to kind of keep some order to this. So top right, that's first row, second column. So we still have this -2, 1, 3. And then, but instead of multiplying that, instead of the first column, we use the second column. So it's 2, -4, 1. So we have -2 times 2 plus 1 times -4 plus 3 times -1, right? Again, I'm taking the dot product of this row with this column right here, okay? So that leaves us with, if we simplify this, that gives us -4 minus 4 minus 3, which that shouldn't be a minus here. Yeah, so that's a mistake I made there. Shouldn't be minus, should be plus. It's just this +1. So that should be plus. And that leaves us with an answer of -5. So in this entry, we get a -5. Okay. And now we can just keep doing this. Okay. Now, once you get good at this, it's just a matter of doing the computation and like practicing it. Okay. But for now, we'll still take it slow. So this, the next row, second row, but still in the first column. So we have second row now, and now in the first column. So we have 3 times 4 plus -2 times 0 plus -3 times 5. So we have 12 plus 0 plus or minus 15. So this answer is -3. So we get a -3 here. And that's what we get there. Okay. So now this next one I'll highlight again like we did before. So let's look for this entry here. So that is now in the second row still. Now we've moved on to the second column here. So those two vectors, or these two, you can think of them as 3-dimensional vectors that I've highlighted. Those are we're taking the dot product of those two vectors. So we get 3 times 2 plus -2 times -4 plus -3 times 1. Okay, so this is 6 plus 8 minus 3. That's 11. So we get 11 in this box here. Again, this is assuming my arithmetic is right. If you notice an arithmetic mistake, feel free to call me out and I'll get that fixed. Okay. That's always a good thing to check too, and especially on online homework, if you're getting the answer wrong and you're not sure why, look for an arithmetic mistake. It's a common error that happens. Okay, cool. So we can kind of keep going at it. Okay, so we have this. We want to get to this one, this entry here. So that's third row, first column. So we do 7 times 4 plus 6 times 0 plus 0 times 5. So this is just 28 plus 0 plus 0. So we end up with 28. Some of these numbers are kind of big, but nothing we can't manage. Okay, now this next one here, that's going to be the same row, but now the second column instead. So that's 7 times 2 plus 6 times -4 plus 0 times 1. So that's 28 minus 24. So that's just 4. So we get a 4 in that entry there. Cool, cool, cool. Almost done. We're in the final stretch now. Bottom left, that's going to be first column, or oof, I should not do that. Last row, fourth row, first column. Okay. So first row is 9, 0, -9. And then first column is 405. So we take that dot product 4 times 9 plus, sorry, I should do 9 times 4. 9 times 4 plus 0 times 0 plus -9 times 5. So we end up with 36 minus 45. So we get negative. I see everyone's comment. Yeah, negative. Let me do this first. -9 here. Okay, so there's a -9 here, but someone pointed out silly arithmetic. A mistake I just made. 7 times 2 is not 28. Let me fix that. So that should be 14. So this should be -10. So that was here. I should get -10. Good catch. That's what I was talking about, especially when you're doing all of these, before we were doing a dot product at a time. Now there's all of these dot products that we've had to do. Inevitably, I'm going to make a mistake on one of them. So just take your time, show your work, so you could figure out where the problem was. Okay. Okay, so last entry is bottom row, far right column. So 9 times 2 plus 0 times -4 plus a -9 times 1. So this is 18 minus 9. So we get a 9 there. 9 in that entry there. Okay, cool. So I wanted you to see me do at least one of these to show you that once you get down to it, the actual arithmetic that happens isn't hard. But as you can see, the bigger the matrix is, the more of it that you have to do, right? We had to do 1, 2, 3, 4, 5, 6, 7, 8 dot products. Basically, and the answer is a 4x2, so we have to do, there's 8 entries here. For each of those entries, we have to do a dot product, okay? And so it's not gonna be necessarily quick, but it's also not going to be super difficult. Okay, the most common mistake you're probably going to make here, if you've gotten comfortable with dot product, is things like I made down here, right, where you do something silly and you forget your multiplication tables. Okay, or you just get on a roll and you move too quickly. Cool. Any questions? So I think conceptually, like if we go back 2 slides, this looked kind of scary, but once we start doing some, we start practicing them, you realize it's not scary, it's just tedious, right? It's just like we have to do all of these dot products, okay? So hopefully you won't have to do too many of this size, but when we're first practicing, it's good practice to kind of see how these work by hand, okay? But you should understand more so than anything, you should understand conceptually what is happening. You're taking, like you all observed, when you multiply matrices, you're really just taking a bunch of dot products. Okay, cool. Okay, so let's look at the properties of this sort of matrix multiplication. So the first thing that I mentioned already is that matrix multiplication is non-commutative. So commutative means that, like normal multiplication, x times y is equal to y times x. But matrix multiplication is not commutative. So A times B is not equal to B times A. In general, there are examples, like you could cook up some example of some 2 matrices that do where you multiply them either way and get the same thing, but that's the exception, not the rule. Okay, cool. Okay, the next I'm labeling this as properties, but we can think of this as like a specific matrix, a nice matrix. So the identity matrix, which we label as I sub n, this is equal to, basically you have ones along the diagonal. We call this is called the main diagonal, and you have zeros everywhere else. Sometimes they just like to draw one big zero there to say that there's just zeros all over around there. Okay, and what does this property have, or what property does this matrix have, I should say? This matrix has the property that if you multiply any other matrix by it on either side, so if, I guess I should say, if A is, if they're compatible in a certain order, then it just turns it back into itself. And then, if you have B over here, then you get B. So maybe A is M by N, and over here B is N by M, or something like that, right? So the difference here is that it kind of, because depending on the order you're multiplying them in, depends on what the size of B is, okay? Or the size of the matrix you're multiplying is. But basically the identity matrix, it's called the identity matrix because it doesn't do anything to the other matrix identity, right? So it just leaves it identical, right, when you multiply them. Okay. So now the inverse matrix is a little complicated. So if A, now it turns out that it has to be a square matrix. So if A is a square matrix, its inverse matrix is has the property so it's also going to be a square matrix of the same size, and basically when you multiply the inverses together in any order, you get the identity back. Okay, so think inverses back when we were learning about multiplication, right? If you multiply a number by its inverse, you always get 1, right? And you can multiply it. So like 2 times 1/2 is equal to 1, but 1/2 times 2 is also equal to 1. And so you get, that's what this is trying to emulate. Now, in practice, this invertible matrix, or the idea of taking an inverse, is actually really difficult for matrices. And finding the inverse is, I should say, if it has an inverse, finding the inverse can be hard. So notice I said if it has an inverse. So not every matrix, just because it's square, doesn't necessarily mean it has an inverse. And we'll talk about that on the next slide. Okay, so let's jump here. So, I forgot actually. I'll talk about invertibility at the end of this slide. But first, I want to talk about how the multiplication works with determinants. So, now again, for this one, you also have to start with square matrices, but the nice formula that we can use is that the determinant of a product is the product of the determinant. So I'm using slightly different notation for the determinant here. This DET, sometimes that gets used, but this is kind of what I'm saying. Oh, so someone's asking me to go back a slide a little bit. So yeah, this last thing that I wrote about the inverses here is going to get used. So what I was saying here, the determinant of a product of matrices is just the product of their determinants. And remember, for determinants, you do need a square matrix. And we can talk about determinants of bigger matrices, but this is going to be nice, especially for 3x3 and 2x2 matrices, which we've been taking the determinants of already. But you can technically take the determinant of like a 4x4 matrix. It's basically the same idea as taking the 3x3, except there's more iterations, because when you do that process, then you end up with a bunch of 3x3s that you have to take the determinant of, and then so then you end up with a bunch of 2x2s, and so then you can finally get the answer. But so it does take some more time the bigger that one really takes more time the bigger it gets. But this is kind of the nice formula that the determinant follows. And if you use this formula, you can actually get something about invertibility here. So a matrix is invertible if and only if its determinant is not equal to 0. Okay. Okay. So this is actually a way that we can look at a matrix. I say look at it, but you also have to do a little computation. The determinant relative to actually computing the inverse, like finding the inverse, would involve a lot of like guessing and checking, because we don't have really many other methods right now. But this here kind of gives us one way. Okay, I know how to compute the determinant of a matrix. If you give me a matrix, I compute its determinant. If I don't get 0, then it's invertible. Okay, then there is an inverse. It doesn't tell you what the inverse is, but it tells you that it has one. Okay, and if the determinant is 0, then it doesn't have an inverse. Okay, again, in a linear algebra class, you'd go more into depth about with this. Okay, and like why that is true. Okay. Okay, give you another second with this slide. This is a lot, right? But one of the things I want, when you're taking notes for this class, when you go to do the homework, I've done some examples of the actual multiplication, but not every problem is just going to be multiply these two matrices. There's going to be some more involved ones. Kind of using sort of the stuff that we discuss here that you write down is going to be kind of the key to getting through some of the homework. Okay. Like there's going to be some questions on the homework where it's like, decide if this matrix is invertible, and you should look at this part of your notes and say, oh, all you have to do is take the determinant. If I get 0, the answer is no. If I get anything else, the answer is yes. Okay. Cool. Okay. And I think there's one more slide after this. Yeah. Oh, so this is exactly that type of problem I was talking about. But you have these 4 matrices. I don't think I have time to go through all 4 of these examples, but let's see this number 1 here. If I want to determine if this is invertible, I just take the determinant of this guy. So the determinant of 2, 1, 4, 2 is equal to 4, right? Or 2 times 2 minus 4 times 1, right? Remember, main diagonal minus off diagonal, and I get 4 minus 4, which is 0. So number 1 is not invertible. It doesn't have an inverse. Okay. Now number 2, I won't get to number 3 because that determinant will just take up too much time, but you can play with that one after class. Okay. We take this determinant, we get 0 times 1 plus or minus 1 times -1. So this is just a positive 1. Oh, I made a boo-boo here. So that should be 0. But it doesn't change anything. Okay, 0 times 0. 1 minus 1 times -1. So that just becomes positive 1. So this is invertible. Okay. Cool. Does that make sense? Again, and then for this one, the 3x3, I won't, I'll save some time by not going through this one in detail, okay? Because the determinant would just take some time to compute, but you just compute this determinant. Is it 0 or is it not 0? And that tells you whether it's invertible or not. Okay, cool. Any questions on this? Any questions on anything we've talked about in this section? Okay, I spent a little longer in this section than I was trying to, but hopefully that that helped us get through it. Okay. And if there are no more questions, I'm going to switch to the next section and spend the last 10 minutes of class getting started in that new section. Okay, so let me save this and open up that next section. Okay, cool. Okay, oops, there you go. It's the beginning of that section. We're going to talk about real valued functions. Fancy word, fancy language that we're going to use for this section. I have some nice pictures here of what we're going to talk about. So you can see here we have a graph of a function that we've been looking at, and then now this is like a fancy like 3-dimensional graph, and that's kind of hopefully what we're going to get out of this today. Well, we won't get through it today, so maybe get out of it tomorrow. Okay, cool. So let's do some like kind of review of functions, right? So functions, they take inputs and they turn them into outputs, right? So you think of them as a machine, you put inputs into it and it spits out an output, right? And these come up in, math all the time. If you can apply it into basically any branch of math that you like, and functions come up all the time. The set of inputs you'd call the domain, and the set of outputs you'd call the range. And the way what we're going to talk about them in this class is all of our inputs are going to be either, are going to have something to do with the real numbers, right? Everything's going to be real numbers. But you might have more than one real number input per in a given function, or more than one real number output in a given function. And so for this, for the notation here, we usually give the function a name that's like a letter. So like F for function is very common. And now the domain is going to be the set of real numbers to so like some n-dimensional space. And then the range is going to be some m-dimensional space. And this is the notation we like to use. So when we were reading this, we'd say F is a function from Rn to Rm. So that's how we'd read this out loud. So F is a function from Rn to Rm. Okay. And now the R's here just tell us that all of the inputs we're dealing with, inputs and outputs, are going to be real numbers. But then this n tells us this is the number of variables input. And then this m is the number of variables output. Okay. So this is the notation we use for functions, and this allows us to talk about a function. This is basically, if we're going to introduce a function without necessarily giving you a nice formula, it's going to be like, okay, F is just going to be some function from R2 to 7 or whatever. That means that it's going to have 2 variables as input and 7 variables as output. Okay, and you can do any combination of inputs and outputs here. Okay, cool. So just some vocab that we use. We call a function of several variables. So you may have heard this class referred to as multivariable calculus. I think that's what it's officially listed as. If the domain is a subset of our n for n bigger than 1. Okay, right? Because if it's n is equal to 1, then that means the domain has just one real variable input, and so that would be a function of a single variable, or of one variable. If we want it to be of several variables, then n needs to be bigger than 1. So several in this situation just means bigger than 1. So that's what we mean when we say a function of several variables. Scalar valued. So now the other two vocab words have the word valued in it. Anytime you hear the word value in a math class, it means the outputs of a function. Okay, so scalar valued function is talking about its outputs. So if the range, so the first definition here was talking about the domain. Now we're going to talk about the range, is a subset of our m for m equal to 1. So maybe I can simplify all of this. Instead of writing rm for m equal to 1, I could just write r1, which we sometimes just call r, right? Or maybe I should say r, which we sometimes just call r1. Okay. And now vector valued, you can imagine, is a very similar thing, but it's still about the range, but instead of getting a scalar out, you get a vector out, which is to say more than one entry. So rm for m bigger than 1. Okay. Pause here for a second. So a function of several variables, the domain takes in multiple inputs, and a function is the values, right? Talking about scalar valued or vector valued means the outputs are scalars, which is to say that the range, the outputs are scalars, or m equals 1. Yeah, so scalar is if m equals 1, and if m is bigger than 1, then we call it vector valued. Can a function be of several variables and vector valued? Absolutely. In fact, we're going to see a lot of those. Basically, you can take any combination of these, right? So the inputs can either be single variable or several variable. The outputs can either be scalar valued or vector valued. And so you can just take any combination. So you could have single variable scalar valued functions, which is what we talked about in single variable calculus. That's what single variable calculus is. And then you can have several variables scalar valued, or you can have single variable vector valued, or you can have several variable vector valued, which is what you're talking about there. So it's all of those combinations of single, several, scalar, vector, right? And so that's kind of, you can have all combinations there. So we're going to start. Let's see, do I have time? I have 2 minutes. I want to give you guys a chance to write all of this down. And I think on the next slide, I have some examples. We're going to look at some functions and determine whether they are, what sort of combination they are. Okay. So let's jump into that, and let's see if I can get through one or two of these in the last minute, and then we'll see the other ones. We'll jump in with those tomorrow. So this first one here, notice it has one input and the output is just a number, right? So if you give me a value of x, x squared is just going to be some number. So this is single variable scalar valued. Okay. That's this first one here. It's only one variable, and the output is a scalar. Okay. This second example has two inputs. So it's we'd call that several variable. And there's still just one output. It looks like you're like, oh, there's X's and Y's, so there should be multiple outputs. But the output itself, if you give me an X and a Y, I square them and add them together, that's just going to be a number. Okay. The hint is that you see in some of these, you get parentheses and commas. Okay. But we don't have any of that up here. So this is still scalar valued. Okay. And I'm out of time with that, but tomorrow we'll jump back into some examples, okay, to finish off these examples.